In chapter 5, we're going to talk about compounds and their bonds. So in chapter 3, we learned about the atom and what made up the atom. Now we're going to start putting our atoms together. Okay. So to start off with, we're going to talk about the octet rule, which is going to dictate how any of our atoms come together. And what this octet rule says is that pretty much all of our atoms are going to try and be like the noble gases, which have a total of 8 valence electrons. So if you recall from chapter 3, that information, we talked about our valence electrons, right? And we talked about our electron dot symbols. Okay, so the valence electrons were those outermost electrons. They're important for us because they are the electrons that do chemistry. They are the ones that interact. So what each of our atoms want to do is they want to gain enough electrons or lose enough electrons to become like the nearest noble gas. That tendency to gain or lose electrons to get a total of 8 is called the octet rule. So we call this the noble gas configuration. So it's going to gain its electron configuration so that it's just like the noble gases. So it's going to be similar to kind of our concept of how we bracketed our electron configurations. Once we got to a noble gas, we said, all right, we're going to put that in brackets. What now is happening for the octet rule is we're taking our atoms and we are going to change them. So the element stays the same, but the electrons start interacting. So say fluorine here, okay, it's 1 away. Notice how you have 2p5, and then we'd have a 2p6. So fluorine is going to gain 1 electron to have this same electron configuration as neon. So the electrons will change. The protons are still staying the same. So we're still dealing with the nucleus of a fluorine. We still have a fluorine atom. We're just changing the number of electrons to be like the noble gases. So when we change the number of electrons, we change the charge on our atom. And we call, when we have a charged atom, so an imbalance in the positives and the negatives, we call that an ion. So an example, we just talked about the element of fluorine. Elemental fluorine has, what, 7 protons? 9 protons, excuse me. 9 protons, has an atomic number of 9. And in the element, we learned in chapter 3, it has 9 electrons. So we have 9 positives, 9 negatives. This is charge neutral. Those 9 electrons, if we look at the electron configuration for fluorine, we have 1s2, 2s2, 2p5, right? So we had 2, 4, plus 5 is the 9 electrons. When we form the ion, fluorine is a negative when it forms an ion. It still has 9 protons because it's still fluorine, but we're going to add that 1 electron to make that a 6. So we have a total of 10 electrons. So we have more negative than we do positive, 1 more negative. So this is going to have a -1 charge. And that's where that negative sign comes in. The electron configuration for our ion, we have 1s2, 2s2, but we're going to add 1 electron to our p's, 2p6, and this is just like neon. In order to determine this charge, okay, we're going to take our number of protons and subtract the number of electrons. And that is something you will want to know for this section, or actually for this entire chapter. So we want to look at the ions that our representative elements are going to form. So we're going to look, again, these are the Lewis dot symbols from chapter 3. We want to look at the ions that all of our group A elements are going to form. And we can do that by looking at electron configuration or looking at the electron dot symbols. So we want to determine the ion formed. We can, again, either do it by our Lewis dot configuration, or we can do it by our electron dot formation. So if we look at lithium, lithium is in group 1A, so it has 1 valence electron, so it gets 1 dot. Its electron configuration, we have 1s2, 2s1. So it's this 2s1 that is our valence electron. So lithium has either the option of gaining 7 electrons to have a total of 8 to be like neon, or it can lose this 1 electron and go kind of backwards in the periodic table and be like helium. So atoms are lazy. They don't want to do multiple things. They want to do kind of the fewest changes as possible. So lithium is going to lose that 1 electron. When lithium does that, it loses a negative. Okay, so kind of think of that as a double negative makes a positive. So it's going to form a +1 ion. And that symbol, the charge goes in the upper right-hand corner. And if it's a charge of -1 or 1, we just put the sign. So here's a plus for fluorine. Here it was a negative. When we have a value, we will put that value in there. We'll see that in the next example that I draw out. But I do want to show that when lithium loses this electron, okay, its electron configuration changes to 1s2. Our next example, if we look at, say, magnesium. Magnesium has, it's in group 2A, so it has 2 valence electrons. Its electron configuration, 1s2, 2s2. It's going to lose those 2 electrons. It's going to lose the 2 electrons in the 2s orbital. So magnesium wants to lose 2 electrons. Losing 2 electrons, oops. So it's losing 2 negatives, makes it a positive. We're losing 2, so we have a 2 plus. When we're writing charges, we want that number first, then the sign. And we do that so that this is different than an exponent. Okay, so we don't want to say magnesium to the positive 2 power. We want to say magnesium to the 2 plus. Okay, we want a 2 plus charge on magnesium. Those are the 2 electrons that magnesium's going to lose to end up having an electron configuration just like helium. Notice that both lithium and magnesium end up with the same electron configuration. Okay, and these are going to have the electron configuration of helium, their nearest noble gas. As we saw here with our example, we can form negative ions. So as we move to the right of the periodic table, we're going to eventually want to gain electrons. So in the example of fluorine, fluorine has 7 valence electrons. It's in group 7A, and it wants, all it needs is just that 1 extra electron to get 8. So fluorine wants to gain 1 electron. It gains 1 negative, so we get F minus. And we see the electron configuration up here. All right, the nice thing about our periodic table is we learned that our electron dot symbols are the same for elements that are in the same groups, right? We talked about group 5A. Nitrogen has 5 valence electrons, 1, 2, 3, 4, 5. Okay, it has 3 blank spots, right? It can gain 3 electrons to be like neon, or it could lose all 5 to be like helium. Atoms are lazy. They're going to do the least amount of change possible. So nitrogen is going to gain 3 electrons for a 3 negative charge. Phosphorus is also going to form a 3 negative charge. Phosphorus also has 5 valence electrons, so it's going to gain 3 electrons to be like argon. So all of our elements that are in the same groups are going to take the same ionic charge. We talked about lithium wants to lose 1 electron to become Li+. Hydrogen is an exception to most of our rules, but hydrogen can lose 1 electron to form H+. We'll talk about that more at the very end of the quarter. Sodium would also be Na+, has 1 valence electron. Magnesium, we talked about, has a 2+ charge. So does beryllium. Okay, so does calcium, which is right underneath magnesium. Aluminum is going to form a 3+ charge. It has 3 valence electrons. Carbon here is in group 4A. So it's in the middle. It can either lose 4 or gain 4. And because that is so much in the middle of what it can do, it actually doesn't usually do either. And we'll talk about the type of interaction that carbon has in a couple videos from now. We talked about nitrogen and phosphorus. They're going to have a 3 negative charge. Oxygen and sulfur, 2 negative. Fluorine, chlorine, a negative charge. And again, this trend goes all the way down the periodic table, not just these 2 rows, but all the way down the periodic table. So let's talk about naming these ions. How do we refer to them? Well, we're going to have different rules for whether or not we form a positive ion or a negative ion. Let's start with the positive ion. We call those cations. So this is going to be a positive charge. These are going to be elements that lose electrons. And they are also typically the metals. And they're on the left-hand side of the periodic table. So remember, we have that stair step kind of splitting our periodic table in half. So anything on the left-hand side. When we name our ions, to name the cation, really easy. We take the element name and then we add the word ion. So for Li+, this is the element of lithium, and we've formed an ion, so we would call this the lithium ion. Mg2+ is the magnesium ion. Fairly easy, straightforward. Negative ions, like this F-, these are called anions. These form a negative charge. These are going to gain electrons. And these are typically the non-metals. So that's going to be the right-hand side of the periodic table. Naming for the anions, not as straightforward, but still very generic. We're going to take the name of the element. We're going to replace the ending of that name with IDE. Okay, so IDE. So if, for example, we take this F-, this is the element of fluorine. So we're going to drop the "ine" and add "ide." So this would be the fluoride ion. All right, fluoride's talked about a lot. They like to talk about that in association with teeth. Okay, so fluoride ion. Oxygen is in group 6A. It has 6 valence electrons. It wants to gain 2. So gaining 2 negative charges. Oxygen is a 2-. Oxygen is the element. Drop the ending at IDE. This is the oxide ion. Nitrogen we talked about is in group 5A, forms a 3 negative ion. This is the nitride ion. It's not always consistent which syllables get dropped. Here we just have the very last syllables. Well, nitrogen actually the last two. If we're going to name this ion, this is the element from phosphorus. We form an ion, we add 3 electrons to it. This is the phosphide ion. It's not the phosphoride ion, it's the phosphide ion. There's a table in your book that shows these ions, pretty much all of the nonmetal anions that we're going to see. It shows all the names of them. For the cations, it shows most of the cations, but it doesn't list them all. Okay. And in particular, we have some exceptions to our naming. It shows the transition metals as having 2 or more different charges. Okay, and the table or image in your book doesn't show all of the different charges. They just show the more common ones. Okay, so do know that there are other examples that are just not listed in that table. So we have exceptions. So from our previous notes, we had talked about these Lewis dot symbols. We only looked at our representative elements, the things that were in group A. We just ignored all of our transition metals, the things that were in group B, because their Lewis dot symbols, their electron dot symbols don't make sense in this picture as we've written it. The reasons for that are very complicated, not going to get into it. You just need to know that these are exceptions to the rules. So they can have multiple charges. Okay, lithium is always going to form a positive charge, but some of our metals in the transition metals can form multiple charges. In addition, we have tin and lead that also fall into this category, and they are over more towards the stair step, but we do consider them in group B. What we're going to do for naming here is we need the element name and the word ion, but we're going to include a Roman numeral to tell us what charge it is. This Roman numeral tells us the charge, and all of our metals are always going to be positive. So we don't have to worry about whether or not it's positive or negative. It's always positive. So if we have 2 examples, we have chromium 2+ and chromium 3+. If we were to follow these rules up here, these would both be called chromium ion. But these are 2 very different species. One has a 2+, one has lost 2 electrons, the other one has lost 3 electrons. That's a big difference in chemistry. Okay, you might think, it's just 1 electron, who cares? The electrons are what do the chemistry. They are the most important to us. So losing an additional electron is a big deal. Okay, and it can completely change the chemistry of what's going on. So just calling both of these chromium ion is not good enough for us. So we throw in this Roman numeral to dictate our charge. Okay, 2 plus is a positive 2 charge, so we want the Roman numeral 2. For this one here, we want the Roman numeral 3 charge. So this would be the chromium 2 ion and the chromium 3 ion. If you need a kind of a review of Roman numerals, the highest we're going to go is a +4 charge. So we have 1, 2, 3, and 4.